So, hexadecimal numbers, as if we need another base number scheme, right? Well, most Western cultures, as you probably are familiar, use the decimal system, base 10, to represent numeric data. We have the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And if we need to represent values higher than 9, we can combine those digits using the notion of place value. So for 10, we have a 1 digit followed by a 0 digit. And we intuitively understand that what we're doing there is we're multiplying the first one by 10 and then adding 0 for a total of 10. Computers do something pretty similar, as you're probably familiar with the binary system, base 2, the difference there being that they are only 2 digits to work with, 0 and 1, and so our place values, instead of being 1, 10, 100, 1,000, as they would be in the decimal system, are 1, 2, 4, 8, and so on. Here's the thing, though. Those zeros and ones, especially if we're being computer scientists and we're doing a lot of programming, and we're working with computers, we're going to be seeing a lot of binary numbers. And those zeros and ones in large chains can be very difficult to parse, right? We can't just look at a string of zeros and ones and necessarily know exactly what it is. But it's still useful to be able to express data in the same way that a computer does. And so we have this notion of the hexadecimal system, which is base 16 instead of base 10 or base 2, which means that we have 16 digits to work with instead of 10 or 2. And it's a much more concise way to express binary information on a computer system. It's much more human understandable. So we have the digits 0 through 9, and then we also have these extra 6 digits, A, B, C, D, E, and F, which represent our notion of 10, 11, 12, 13, 14, and 15 in decimal. Sometimes, by the way, you'll also see these A through Fs as capital A through F, which is the way I tend to do it. It's just my preferred style, but either is fine. They both represent pretty much the same thing. So why is hexadecimal cool? Why do we need to use this other additional base? We already have 2 and 10. Why do we need 16? Well, 16 is a power of 2. And so each hexadecimal digit, 0 through F, corresponds to a unique ordering or unique arrangement of 4 binary digits, 4 bits. And so in that sense, we can express very long, complex binary numbers in hexadecimal in a much more concise way without losing information or having to do particularly cumbersome conversions on those numbers. So as I just said, each hexadecimal digit corresponds to a unique arrangement of 4 binary digits. So the binary string 0, 0, 0, 0 corresponds to hexadecimal digit 0. 0, 1, 1, 0 corresponds to hexadecimal digit 6. And 1, 1, 1, 1 corresponds to hexadecimal digit F. If you're looking at this chart, particularly if you're looking at the left side of the chart, you can already see there's a bit of an ambiguity problem here, right? Decimal 0 is pretty much indistinguishable from hexadecimal 0, other than the fact that it's under a column that says hexadecimal, but we probably won't always have that column there. And so generally when we were expressing numbers in hexadecimal notation to clearly distinguish them from decimal notation, we usually prefix them with the prefix 0x. 0x means nothing in reality. It's just a clue to us as humans that what we're about to see, or what we're about to have to start parsing, is a hexadecimal number. Obviously, for the higher digits, A, B, C, D, E, and F, which correspond to 10 through 15, it's pretty unambiguous that that's a hexadecimal number. And in fact, any hexadecimal number that has letters in it is probably pretty obvious as a hexadecimal number. But still, for the sake of clarity, it's always a good idea to prefix every time you refer to a digit as a hexadecimal number by prefixing it with 0x. So binary, as we said, has place values. There's a 1's place, a 2's place, a 4's place, and an 8's place. And decimal also has place values, the 1's, 10's, 100's, and 1000's that we all may recall from grade school. And hexadecimal is no exception here, really. It also has place values, but instead of being powers of 2 or powers of 10, they're powers of 16. So when we see a number like this, we pretty clearly know it's 397, right? Well, if we see a number like this, we know this isn't 397 anymore. This is the hexadecimal number 397. It's not 397. It means something different because we're using powers of 16 as all of our place values instead of powers of 10. In fact, the place values here would be the 1's place, the 16's place, and the 256's place, which correspond to our idea of a ones place, a tens place, and a hundreds place if the number was 397. But since it's 0x397, we have a ones place, a 16's place, and a 256's place, or a 16 to the 0 place, which is 1, a 16 to the first power place, 16, a 16 squared place, 256, and so on and so on and so on. So this number is really 3 times 16 squared plus 9 times 16 plus 7. I didn't do the math here, but it's not 397. It's much larger than that. Similarly, we could have 0x_ADC. Well, that's a times 16 squared, or if we translate that to our notion of decimal numbers, that's 10 times 16 squared, plus d times 16, or plus 13 times 16. And don't worry if you haven't memorized that d is 13 or anything like that. There's not too many of these letter digits, and it'll become intuitive pretty quickly. So again, this is 10 times 16 squared plus 13 times 16 plus 12 times 1, so 0x_ADC. So as I said, every group of 4 binary digits corresponds to a single hexadecimal digit, and so it's actually really easy to change back and forth between hex and binary. If you have this long string of binary digits, all you need to do is start grouping them right to left as groups of 4, and then you can consolidate them into hexadecimal numbers, severely limiting the number of digits you have to process mentally. Instead of 32 zeros and ones, as we'll see in a second, you might be able to get it down to just 8 hexadecimal digits. It's a lot more concise. The charts a few slides back will help you to kind of figure out this mapping, though you'll, again, memorize it pretty quickly. And we'll go through an example right now. So if we have a number like this really large binary number, or what appears to be a large binary number, and the only reason I say that is because it's just so, it's a behemoth, right? There's just so many zeros and ones there. But we probably don't really have a sense of what the magnitude of this number really is. We don't have any idea what it would correspond to in decimal, and in fact, we won't even see what it corresponds to in decimal right now. But we might be able to express this in a way that would give us some more information about just how big this number is. So let's go through that conversion process. The first thing we need to do is we want to group these digits out into groups of 4, starting from the right and working to the left. Now, there happen to be 32 digits here, which means we have a nice clean break of 8 groups of 4. So we have now, and remember that each group of 4 here uniquely corresponds to a hexadecimal digit. So we'll start, again, building our number from the right and working left. Well, what's 1101? Well, if we do the math out in our head, we have 1 in the 8's place, a 1 in the 4's place, a 0 in the 2's place, and a 1 in the 1's place. That's 8 plus 4 plus 1, which we would know as 13, but we probably wouldn't write 13 out because we're working with hexadecimal. We need to convert it to the hexadecimal equivalent of 13, which is D. 0011, well, that's a 0 in the 8's place, a 0 in the 4's place, a 1 in the 2's place, and a 1 in the 1's place, so that's 3. And we can keep doing this again. We have here 9, and then 11, but that's B, recall, 2, 10, or A, 6, and 4. And so that very large string of zeros and ones at the top is more concisely expressed in hexadecimal as 0x46A2B9 3D. Well, okay, we've learned a new cool skill. What's the point? Well, you might not use this all the time. As we're going to soon see, we use hexadecimal quite a lot as programmers, not necessarily for the purpose of doing math with it, but because a lot of times memory addresses in our system are represented in hexadecimal. And so it's a really concise way to express otherwise cumbersome binary numbers. And so again, you're probably not going to do any math with it. You're not going to be multiplying hexadecimal numbers together or doing anything weird like that. But it is a useful skill to have so that you can express and understand memory addresses and other ways of using data in C. I'm Doug Lloyd. This is CS50.